Hey everybody, I know that you love a good math video, but we can't afford a day of not doing it, and obviously I'm not there, so I'm just gonna teach this to you in good old online learning format. So here we go. We talked yesterday about sequence and like that's a pattern of numbers, and today we are gonna get a little bit do a couple more things. We're going to learn what a recursive formula is versus the explicit, and then summation, which is exactly what you think it is, which is adding stuff up. So yesterday we talked about if you have a sequence of numbers, A1, A2, A3, and so on, and then down here you have an AN, the one before that would be N minus 1 subscript, and the one after that would be plus 1, and so on. We did explicit formulas where you would say, well, here's the first, second, third, and then like ultimately the nth term. And an explicit formula, you could plug the term number in to get that value. You would think, what do I have to do to this number to get that number? What do I do to 3 to get that number in the list? That's actually harder than what we're doing today, because today we're going to do when the pattern used to describe a sequence is related to the previous term. So instead of trying to figure out how to tie it back to the term number, you just look at the number before it, which was easier yesterday too. You'd be like, oh, you just add 2, you just do this, you just do that. So this should be easier. The formula used to describe it in this way, where you're saying, hey, take the number before it and do this to it. That's going to be called a recursive. So recursive versus explicit. Explicit, you plug in the term number. Recursive, you build on the previous term. So notation for the previous term, and we talked about this yesterday, is if you're trying to find this, the previous term is A and then subscript N minus 1. You're saying take one step back. So if this is my A sub N, I always think of it like this. This is one step back. This is 2 steps back, This is one step forward, and if I had another one, I'd go one step forward from there. So as you go to the right, you're taking steps forward and adding to the subscript. As you move to the left, you're taking steps away and therefore subtracting into the subscript. So these are pretty easy if they don't ask you for something too far down the line. We did this yesterday. Find the first 4 terms using the recursive formula. Recursive formulas, you're going to have 2 equal signs. So they have to tell you like where to start. And then there's going to be a rule telling you what to do, but you're not doing this to the term number. You're going to do to the previous term. So in this case, it says start with 2. A sub 1 is 2. Then it says take the previous term and add 5. So if I take 2 and I add 5, I'll have a 7. If I add 5, I'll have a 12. If I add 5 to that, I'll have a 17. And you could keep going pretty easily. The trouble with recursive is these guys. I don't really want to find either one of these because you have to know all the previous terms. So you would need, like in this case, the 99 previous terms, because you can't build on the term in front of it if you don't know the term in front of it, and then you have to do like this long string of, add 5, add 5, add 5. So that's where explicit came into play, where this would be better to do with an explicit formula where I can just plug in the 100 and plug in the 16. So same thing here. This is saying the first term is a -3. You should do this to it. So to get to the next term, I take 2 times the previous term and add 1. So that's this guy. So that's going to put me at -5. Then to move to the next step, I take 2 times the previous term and add 1. So -9. To get to the next space, I take 2 times the previous term and add 1. So I'm at -17. So you're just moving more in like a chain, one step to the next. You are not thinking back to the term number. Like this would be term number 1, 2, 3, 4. I'm not trying to turn those numbers into the numbers I see in the list. I'm just going from one term to the next. Now this is kind of unique, and this comes up on our quiz, so we want to make sure we know what we're talking about. Here, they're telling me the first term is a 1, the second term is a 3, and then look at this rule. This is saying, hey, if you want to fill this spot, you have to go 1 back, like 1 term back, plus you add 2, the number that's 2 back from where you are. So for me to fill this spot, it's asking me to add the 3, which is the previous term, to the one even before that, which would be the 1, putting a 4 in here. So to find the 7, to find the next number, here, my dog's gonna drink loud. I'm gonna add the previous term plus the one that was 2 back. So it's telling you to add the 2 previous terms. So I get the 7 that I already ruined the surprise of later. Dolly, I'm making a math video. You're so rude. All right. Then that was filling in the terms given the recursive formula. Now we have to write the recursive formula. Basically, you need to tell them where to start. So you're saying start here. So one part of your equation has to be, hey, A1 is going to be 1. Okay. And then what's happening as you go from term to term? You're adding 2 to the previous term. So I would write start at 1, and then any term is going to be the previous term, add 2. So you're always going to have this notation in a recursive because you're always building on at least the term that's 1 back, maybe terms that are 2 back like we saw. So if I look here again, this is also starting at a 1, but this one's a little bit tricky. Because if you look at the pattern, you actually have to do something that we already saw up above. There's not a pattern that goes from 1 to 1 to 2 to 3, but this 2 is the sum of the 2 numbers in front of it. This 3 is the sum of the 2 numbers in front of it. 5 comes from adding the 2 and the 3. 8 comes from adding the 3 and 5. 13 comes from adding the 5 and 8. So my next number, if I was going to fill it in, would come from adding the 8 and the 13. So I'd have a 21 next. So you're thinking you have to add the 2 previous terms. So that's how you get through this sequence. Okay, so I not only need to say what the first term is, I need to say what the second term is. And in this case, it's going to be, well, actually, here, I'll do it this way. Sorry. This will make it easier. I'm going to go ahead and say, hey, all I need to do is take the term that's 1 back from where I am, the previous term, and add that to the one in front of it. So again, if we were writing out our list, we would have like A1, A2. Somewhere down the line, we'd have A sub n. The one before that would be 1 back. The one before that would be 2 back. And in this case, we're having to add the one that's 1 in front of it to the one that's 2 in front of it. And that is our rule. That's come up twice in the notes, so make sure you kind of understand that concept of maybe having to add 2 together. So this series up here, 1, 1, 2, 3, 5, this is the Fibonacci numbers. And if you haven't ever seen anything about that, I'm probably spelling this super wrong. You can look it up, but it's like a weird pattern that exists in nature and science. If you Google it, it's actually kind of interesting, and go down that rabbit hole if you're bored. So, which you guarantee you're bored, you're watching a math video. Okay, so this we've seen also, and we knew how to write it explicitly, but now we have to say, okay, start with 1. And then what do? How do you get 1 to turn into -1? Well, you multiply it by -1. How do you get -1 to turn into +1? You multiply it by -1. So and then our second equation is going to say, well, once you start at 1, to get all the other terms, take -1 times your previous term. And so you're saying, hey, start at 1. Now to get the next spot, take your previous number times -1. To get your next spot, take your previous number times -1, and so on. Keeping in mind that you always have 2 equal signs when you are doing the recursive, because one says what to start with, one says what to do. Here it said start with 1, here it said add the 2 previous terms, and so on. So recursive functions, you need to be able to generate the terms, like find out what the terms are, like we did right here. And then you need to be able to write the recursive formula. Okay, so the other part of the notes is supposed to be summation. Summation is literally adding. So this is sigma, this symbol that you see, it's a Greek letter. We also call it the summation notation. The key is the sum. It's used to add the terms. So it's just like yesterday where you generate the terms, but then you add them together. So here's what the notation looks like. This can be an I or a J or a K or an L, N, O, P, Q, all of them. But they use I a lot. And all it's telling you is that this is going to be the first number to plug in. So this is going to give you like a rule right here. This is going to be an explicit formula, so we can find the terms by plugging in the term numbers. So this is going to be the explicit formula. And this is basically the number that you start plugging in. And this top number is where you stop plugging in. So this is going to be like my first term. It will generate that. And this is going to be my last term. So, okay. Here it says evaluate the following. Keep in mind that evaluate has a root word of value. So I should just get a number answer. That's true with everything that we do. When it says evaluate, it's asking you to find the number answer. So here's my rule. And I'm going to start by plugging in a 1. So 3 times 1 generates a 3. But I'm not creating a list. I'm creating a sum. So I add the next term. And then the next term is 3 times 2. So that's 6. Then 3 times 3. 3 times 4. 3 times 5. And I stop because it says to stop at 5. So I plugged in here to my rule. Here the rule was 3 times your number. So I plugged in a 1, then a 2, then a 3, then a 4, then a 5, then I quit because that's my stop number. So if I work these out, 3 plus 6 plus 9 plus 12 plus 15, I'm going to end up with a sum or total of 45. I'm adding up the terms. Okay, so this one, be careful, because this one doesn't actually start with 1. It starts with 3. So I would have, my first term is going to be 1 plus 3 squared. Then I'll be adding 1 plus 4 squared. Then I'll be adding 1 plus 5 squared. And I'll stop when I get to 1 plus 6 squared, because this is my stop number. This is telling me to stop here. This is telling me to start here. All right. So when I do that, I'm going to generate 1, 2, 3, 4 terms, and then I'm going to add them up. So if I do 1 plus 3 squared, I'm going to get 10. 1 plus 4 squared is 17. 1 plus 5 squared is 26. 1 plus 6 squared is 37. And the sum of all of those is 90. So it said to evaluate, that's my value, my number. This one could take you a while because you're supposed to start at 1 and stop at infinity. Okay, well, yikes. Nobody wants to stop at infinity because you never get to stop. So let's take a look, see if we can establish a pattern. 3 over 10 to the first power would be 10, which is 0.3, plus 3 over 10 to the second power would be 100, which would be 0.03. My third one will be 3 over 10 to the third, which is 1,000, which is 0.003. If you keep doing that out to infinity, look what's going to happen. If you add this to the second one, to the third one, and then probably the fourth one, you ultimately are creating a 0.33 repeating. And if you want the actual value of that, we know that 0.33 repeating is a 1/3. So if you added these up, what happens too, if you think about this, these are getting smaller and smaller as you go, because 3 out of 10 is not bad, but 3 out of 100 is very little. 3 out of 1,000 is littler. 3 out of 10,000, 3 out of 100,000, and so on. So you're basically saying, hey, these numbers towards the end are getting so minuscule that when I add them up, I just get 0.33333 forever, which is approximately a third. All right, we have vowed not to panic when we see fractions, so let's not. How do you do this? How do you use sigma notation to write the sum? Well, you got to figure out what goes on the bottom, what did I plug in first, where did I stop, and what is my rule? Here's what I do. I look at each of the terms they gave me. They all have 5 on top. They all start with 1 plus, and then the only thing changing is this. And keep in mind that this is my first term, second term, third term, and this must be my 15th, because all they're doing is putting the term number in for that second spot. That tells me what I need to know. I started by plugging in 1, I ended by plugging in 15, and the formula or the rule was 5/1 plus I. Because it's saying to start plugging in a 1 where the I was, and then go until you plugged in a 15 where the I was, which is that last one. Here, this one's kind of tricky. The pattern's hard to see. But if you look at these numbers, 2, 4, 8, these are powers of 2. Now, this first one looks really weird because it's not a fraction, but anything that's not a fraction is over 1. 1 is 2 to the 0, 2 is 2 to the first, 2 to the second, 2 to the third, and if I bust out my big brain, 128 is 2 to the 7th. Okay, so I have to figure out how to write what's going on. Now the problem is, this is supposed to have an n value of 1. So, and this is supposed to be 2, 3, 4, but the problem is, this is not 2 to the first power, it's 2 to the 0. The next one's not 2 to the second, it's 2 to the 1. This one's actually 2 to the second, 2 to the third. So the top number is always 1 in my problem. The bottom numbers are 2 to a power, but the power isn't equal to the term number, it's equal to 1 less than the term number. Also, I see that they're going plus, minus, and so on. Okay, well, we've done that before. And then the way to do that is to take -1, and then since it starts positive, this is directly from my notes yesterday, my power is going to be I plus 1. And the only reason I'm not using an n is that they are using the I in the sigma notation. Doesn't matter. They could be all n's, all k's, but as long as I started with I got to stick with it. So the first number that I would have plugged in here was a 1. But what about here? If this is a 7 and that's 1 less than the number I plugged in, I must have plugged in an 8. So my first term was I got by plugging in a 1, and then my last term I got by plugging in an 8. The -1 to a power of I plus 1 keeps my positives and negatives alternating and starts me with a positive. All right, so let's get a rule. This one's kind of tricky also. Here I can see that I have 1, 2, 3, 4, 5, 6 terms. So here I know that I'm starting by plugging in 1 and I'm ending with a 6. But I got to get a rule. Start to look for the same things. Like the last one was 2, 4, 8, blah, 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 and that was powers of 2. So how about this time when I have 2, 4, 8, I consider powers of 2. Here in my first term, 2 to the 1 gives me 2. 2 to the second gives me 4. 2 to the third gives me 8, and so on. So all I'm doing is I'm taking for that bottom number 2 to the power of the term that I'm on. So this is the the sixth term, and 2 to the sixth gives me 64. Now I need a rule for the top. The rule for the top is honestly super tricky. We talked about it briefly yesterday, but again, once you see it, keep in mind, like, now it's fair game. Here, keep in mind, we're still using these guys down here. 1, 2, 3, 4, 5, 6. We did this one yesterday. This is 5 factorial. I happen to be on the 5th term. So, testing that theory, this is the 4th term. Is 24 4 factorial? It is. Is the 6 going to be 3 factorial? It is. Is 2 2 factorial? Yup. Is 1 1 factorial? So all of the top is the term number factorial. I think that's pretty tricky. But again, we learned yesterday, hey, if it's going back plus or minus, use this tool. And here we're looking at those numbers thinking, okay, if I can kind of remember that factorial is an option, then maybe I can look for that pattern if I'm struggling to see a different pattern. Almost done. Here's just some properties of sums. This is just saying, hey, if you start by plugging in a 1 and you stop at n, what will happen if you have c here? Now, c here is meaning a constant, like just a number. So check it out. What if I had like I equals 1 to 4 of 3, which is just a constant? Well, every term is 3. The first, the second, the third, and the fourth. So I, said 4, wrote 4. They're all 3s. That adds up to 12 because I had 4 terms and every one of them was a 3. So what this is going to tell me is I'm just going to end up taking that constant times the number of terms. Here, I have a constant times a rule. You can actually pull that out in front, and then you can just find the rule, get the sum for that, and whatever you have at the end, multiply it by c. Like here, if you have the sum of 2 separate things, you can split them up if that's easier. So I could find just the sum of these terms and then add or subtract the sum of the terms from the other part. So these are just like, you can keep them together, you can split them up depending on what suits your needs. And then this last one, this one's kind of, it's called an infinite series for obvious reasons. It goes on forever. And so I'm going to have A plugging in 1, then A plugging in 2, then A plugging in 3. And I'm going to keep going until infinity, which you actually can't keep going to infinity. So you can't really add up all of them right now, but we can add up part. And when you add up part, it's called a partial sum. So if you're asked for the third partial sum, it means you can't do the whole sum because it goes to infinity, but you could do the first 3 parts. So if you're looking down here and it asks you for the 4th partial sum, that would be the instructions. You just say, oh, well, that's going to be 3 over 10 to the first plus 3 over 10 to the second plus 3 over 10 to the third plus 3 over 10 to the fourth because it said 4th partial sum. We already did this. Then we knew this was 0.03, 0.003, and 0.0003. And when you add up just those first 4 terms, you're going to get 0.3333. So that is my partial sum. Not 1/3, but the 0.333, because it's not rounded off. It just stops after just that first partial sum. If you keep going forever, so if I did actually go to infinity, I'd have 0.3333 forever, and that's where we could say, oh, that's a third. But this is just that fourth partial sum, adding up 4 parts, done. So that concept of sums and partial sums, and then the idea of recursive should get you through the 8.1b, or it might say 8.1 day 2, but I kind of feel like it's B. That is the worksheet that you want to be working on. And another reminder that I'm not actually reteaching this on Friday. We're going to go ahead and look at the next section. So make sure you know what you're doing on this. If you decide to take today off in class, 1, don't be a jerk to the sub, please. And 2, know that you got to do it at home tonight, because tomorrow I'm going to assume you know it and carry on. Have a good day, you guys. Bye.